3.8, page 192. All right, page 192 is higher derivatives. And what they're talking about here is we already know how to find the first derivative, but you can also find a second derivative or a third derivative or a 27th derivative. And so that's what we're talking about with higher order derivatives. The notation that they're going to use for this, you'll notice that we have two different ways of writing that because we have the Leibniz notation and we have the Newton notation. But one way, you know how we typically write f prime for the derivative. If there are 2 prime marks, that means the second derivative or the derivative of the first derivative. If there are 3 prime marks, that means the third derivative or the derivative of the second derivative. And if there are 4 marks, then that means the fourth derivative or the derivative of the third derivative. Additionally, our alternate notation, like this is first derivative, so this is second derivative. This is first derivative, so this is second derivative. So let's look at example number 3. All right, example number 3, we have a cubic function, and they ask us to find the first derivative, which we've been doing for a while now. So if we took the first derivative, derivative of x cubed is 3x squared, then this guy, negative 12x, right? And then this, minus 5, and then plus 0, right? So 3x squared minus 12x minus 5. If we want the second derivative, then the second derivative is literally just the derivative of the first derivative. So I could say the derivative of 3x squared is, and then negative 12x, and then negative 5. Yeah, so we get 6x minus 12, right? And then if we wanted the third derivative, that would just be the derivative of the second derivative. So what would that be? And then if we wanted the fourth derivative, that would just be the derivative of the third derivative. So that would be, and if we wanted the fifth derivative, it would be, what's the derivative of 0? 0 is a constant, so the derivative of 0 would just be 0, right? And we could keep right on going. Like the fifth derivative would be 0, the sixth derivative would be 0, it would just keep right on going. So from there on, we literally could say, if you were trying to find the derivative of the function where we were looking for the fourth derivative or higher, so this number is greater than or equal to 4, then every one of those derivatives is going to be 0. So in that case, the derivative got easier to take as we went higher. Of course, that's not always going to be the case, but it's nice when it is. All right, so look at the next one. For the next one, we have a product of x times cosine x. So let's find our first derivative. We're going to have to use product rule. So we'll do first times derivative of second. What's the derivative of cosine? All right, plus second times derivative of first. What's the derivative of x? 1. So we can simplify that a little bit. Negative x sine x plus cosine. All right, then we want to take the second derivative. And we kind of get the idea when we took the first derivative, this got a little more complicated than it was originally. So if we take the second derivative, probably same thing going to happen. But let's start with this first piece. We have a product again, so we're going to do first times derivative of second plus second times derivative of first. So we'll do first negative x times derivative of second. What's the derivative of sine? And then plus second sine times derivative of first. So what's derivative of negative x? Negative 1. All right, then let's come down here and look at this next piece. What's the derivative of cosine? Negative sine. So simplify a little bit. We've got negative x cosine x, negative 1 times sine x, and negative 1 times sine x. So can I simplify that at all? Negative 2 sine x, right. All right, so now we get the feel for how those higher order derivatives work. Let's look at some applications of them, because we've been focusing on this whole chapter on applications of derivatives. So there are some really cool applications for our higher order derivatives as well. Let's go back to the idea of particle motion. All right, for particle motion, example number 2, the position of a particle is given by this equation where t is measured in seconds and s is measured in meters. So we want to go through and find the first derivative, the second derivative, and the third derivative. Now, we've already talked about that the first derivative is velocity. Because if we're talking about the rate of change of our position, how quickly we're changing our position, that is our rate. That's our velocity. So if we go through and we take the derivative, the first derivative is velocity. We've done that before. If you are traveling at a constant velocity, let's say that you're traveling 55 miles an hour, and then you change your velocity so that you change it to 65 miles per hour. What did you do? You accelerated, right? So the rate of change of velocity is acceleration. Now, sometimes it's acceleration, sometimes it's deceleration, but either of those is a rate of change of your velocity. We call it acceleration. So for that reason, the rate of change of velocity, the derivative of the first derivative, the second derivative will be acceleration. So my second derivative will be acceleration. So we could go through then and take the derivative of our velocity equation, and that would give us our acceleration equation. Now, if you are accelerating and all of a sudden somebody jumps in front of you and you have to slam on the brakes, that is a rate of change of your acceleration, right? And when you do that, you are going to jerk, right? So that's an easy way to remember that the rate of change of acceleration, or the derivative of acceleration, is jerk. So the third derivative is jerk. So first derivative velocity, we already knew. Second derivative acceleration, or the rate of change of velocity, the derivative of velocity, is acceleration is second derivative then. And then third derivative, the rate of change of acceleration, the derivative of acceleration will be jerk. Our third derivative will be jerk. All right. So for example number 2, we went through and we found each of those. But then for A, it says, what is the acceleration after 4 seconds? So if I wanted to know the acceleration when t is equal to 4, then I can just put 4 in the place of t. So what am I going to get when I put 4 in place of t? 12. Right. Now, these equations were fairly easy to work with, fairly straightforward. But let's say that you had something maybe like the prior example that we were working with, where you had a trig function, and each time we took the derivative, it got worse. Like when we took the second derivative, it was already getting pretty bad. I don't really want to sit there and take the third derivative and then start plugging in values. And so there is a way that I can do that on my calculator, right? We've done this before, but just for review, if I have my original function, here is my my position function right here, I could type in the derivative in y2. I could type in 3t squared minus 12t plus 9. But remember that I don't actually have to calculate that derivative for my calculator to be able to graph it. We've seen before that we can put in, if you go to math and you go down to n derivative, in the old operating system it'll show up like this, in the new operating system it'll show up like this when you hit that button. So in the old operating system, you could tell it y1 if you didn't want to retype that whole equation, or you could retype that whole equation right there, comma the variable that you want it to be in terms of, which is x, and then comma the value that you want it to use. And I don't want it to use one value, I want it to use every x value, so it graphs the whole thing. On the new operating system, when I do n derivative, it looks like this, and again, I could either retype the equation or just type y1, so it uses that equation without me retyping it. And then I'm going to tell it x equals, again, every value of x. Instead of giving a number there, I'm going to tell it let x equal every value of x, so it graphs the whole thing. So when I do that, and I'm going to tell that second one to graph in bold just so that I can see it, here's my original position function right here, and that makes sense. That looks like a cubic. And then here's my velocity, my first derivative, and that makes sense because that looks like a quadratic. So nowhere did I tell it 3t squared minus 12t plus 9. I didn't give it that equation, but my calculator is able to calculate that and graph it for me. So if I wanted to know the entire graph of acceleration, I could ask my calculator to do that. I could come down here in y3 and tell it take the derivative of what's in y2, and we'll do that in a minute. But if I'm only interested in one value, like we didn't need the whole acceleration equation, we only needed the acceleration at 4, right? So what I could do is I could say, okay, since acceleration is the derivative of velocity, right now in y2, I'm graphing velocity. So I'm going to go to my graph, and this is really important. I'm going to go to my graph, and I'm going to make sure that I go to number 2 on my graph, because if I'm on number 1, then it's going to do whatever I tell it to do in the calculate menu. If I'm on what's in y1, it's going to calculate the derivative or the maximum or the minimum or whatever I tell it on that equation. I need to use my arrow keys to scroll down between my equations to get to the one that I want. So I would tell it, hey, I want you to use the equation that's in y2, not the equation that's in y1. And then I'm going to tell it to do the derivative, and it will ask me when x is equal to what, and I could tell it 4. And you'll notice then that it will tell me the derivative is 12. So that would be another way, a fast, easy way, if I had my calculator and I didn't want to actually calculate the first derivative and the second derivative and then plug 4 into that second derivative. I didn't have to calculate any of that here, right? I put in the original equation only and let my calculator do all that work. So that would be great if I had my calculator. Just wanted to make sure that you connected those dots, that you had that option. All right, so then over on page 193, they show us the graph. You know, we just looked at a second ago. Here's the graph of the position, and here's the graph of the velocity. So they show us that in the textbook as well. Your position is red. Your velocity equation is right here in blue. And then if we also had asked it to graph the equation of acceleration, there it is in yellow. So we should be able, if they give me the original function, we should be able to graph the first, second, and third derivatives. Remember the way that we did that. Let's say that I'm looking at this position function right here, and I want to graph the derivative. The way that we've done that before is we did horizontal line test, not vertical line test. We want to look at where we can draw horizontal tangent lines, right? So wherever I can draw a horizontal tangent line, like right here, there would be an x-intercept on my derivative, right? Horizontal tangent line right here, there would be an x-intercept on my derivative. Then we looked at where was the original function increasing. So original function increasing from 0 to 1, my derivative should be positive there, and it is. Original function decreasing from 1 to 3, derivative should be negative there, and it is. Original function increasing from 3 to 5, derivative should be positive there, and it is. Let's say that we were looking at the blue graph and trying to graph its derivative. Our blue graph was velocity, so if we wanted to graph its derivative acceleration, we could say, okay, where can I draw a horizontal tangent line? So that's the only place I can draw one, so I would have an x-intercept on the derivative there. And then I could say this entire function was decreasing from 0 to 2, so the derivative would be negative there. And then it was increasing from 2 on, and so the derivative would be positive there. And remember that you can also plot strategic points where you need to fill in gaps. So if they give me the original function, we should be able to graph the first derivative, second derivative, however far they ask me to. We also should be able to look at a graph when they give me one something like this and be able to identify, okay, which one of those was the original function, which was the first derivative, which was the second, which was the third. You know, sometimes it's obvious. Like in this case, I can see I've got a graph of a cubic, and then I've got a graph of a quadratic, and then I've got a graph of a linear. If it went 3, 2, 1, it's pretty easy for me to see where the derivatives were taken, but that won't always be the case. So I should be able to do what we did with, okay, where would I have a horizontal tangent line? The only other graph on this piece of paper that has an x-intercept there is that blue graph. That has to be, the blue graph has to be the derivative of the red graph kind of thing. So I should be able to look at the graphs and identify the derivatives in that way as well. Okay, so for B it said graph the position and the velocity and acceleration of those three. So whether we graph them by hand or we graph them on our calculator, we've kind of looked at both of those scenarios. Then for C it says when is the particle speeding up and when is it slowing down? And this is something new for us in relation to particle motion we've not seen before. So look there in the middle of 193 at the discussion that they have for C. It says the particle speeds up when the velocity is positive and when the velocity is increasing. Now that makes sense. If the velocity is positive, meaning it's already going forward, and then it's increasing, that means that it's speeding up, right? Well, that would only be true when both velocity and acceleration are positive. The particle is also speeding up when the velocity is negative, meaning it's going backwards, and it's decreasing. That would be when velocity and acceleration are both negative. So in other words, the particle speeds up when the velocity and acceleration have the same sign because the particle is being pushed in the same direction it's already moving. But the particle will slow down when velocity and acceleration have opposite signs. So in C, when it says when is the particle speeding up and when is the particle slowing down, I need to analyze velocity and acceleration. So I'm literally going to go through and say, let's talk about velocity first. So if I'm looking at the graph of velocity, that's the blue graph right here, I could say, okay, I have an x-intercept at 1 and at 3. So down here, x-intercept at 1, x-intercept at 3. The velocity graph was positive from 0 to 1, so positive there. It was negative from 1 to 3, so negative there. And it was positive from 3 to 5, so positive there. Then I'm going to look at acceleration. Acceleration was the yellow graph. So I can say, okay, it had an x-intercept at 2, and it was negative from 0 to 2, so negative there, there. And then it was positive from 2 to 5, so positive there, there, and there. So now let's go through and look at those. It is, the particle is going to be speeding up when the velocity and the acceleration have the same sign. So right here, they're both positive, so that's speeding up. And right here, right here they're both negative, so that's speeding up. And right here they're both positive, so that's speeding up. Anywhere they have the same sign. Then I can go back and say, okay, it's slowing down where they have different signs. So from 0 to 1, I have a positive and a negative, so slowing down there. And from 2 to 3, I have a negative and a positive, so slowing down there. So signs different from 0 to 1, slowing down. Signs the same from 1 to 2, speeding up. Signs different from 2 to 3, slowing down. Signs the same from 3 to 5, speeding up. So if I wanted to graph that on my calculator, we've already alluded to this earlier today, but if I wanted to generate that exact same graph on my calculator, we had already put the original equation in y1 and the first derivative in y2, so then I can ask it to do the derivative of y2 in y3. I just tell it, take the derivative of the equation that I have in y2 for every single value for x. So this is my original function, this is my first derivative velocity, this is my second derivative acceleration. And you can see I can get my calculator to generate an identical graph to this one up here, and I'm not telling it any equations other than the original that's given. I'm not actually having to take the time to calculate out all those derivatives and do horizontal tangent lines and increasing, decreasing, positive, negative. I don't have to do all of that if I have my calculator. I can save myself all of that time and energy. Okay. So the things that we have added to our understanding of particle motion today are the second derivative is acceleration, the third derivative is jerk, and your particle is speeding up when velocity and acceleration have the same sign. It's slowing down when velocity and acceleration have a different sign. So I made you a master sheet of particle motion and gave that to you, told you throw it in the front of your notebook somewhere that it'd be easy for you to find, and mentioned to you at that point we didn't know probably half of the stuff that was on that sheet, that we would just keep adding to it as the year went. So these are some things that are already on your sheet that now we could kind of check off and go, okay, I understand now what we're talking about when we see those things. Okay? So we know velocity, acceleration, jerk. We know when the particle is moving forward, when it's moving backward, when it's at rest, when it's speeding up, and when it's slowing down. Okay. All right, then the last thing that we want to look at is higher order of these derivatives. Now I know we've looked at like a first derivative and a second derivative and a third derivative, but we want to look at a 27th derivative, all right? The only time that we can do this is when I have something that follows a pattern, like the derivative of cosine is negative sine. The derivative of negative sine is negative cosine. The derivative of negative cosine is sine. the derivative of sine is cosine, I'm back to where I started from, right? If I kept doing those derivatives, I would get the exact same things all over again. So when it is cyclic like that, where I can say, hey, there are 4 of these in a cycle and then it starts repeating, then I can take whatever this derivative is and divide it by that cycle. And I get 6 remainder 3. That means that I'm going to go through 6 complete cycles of these, and then I would be 3 into the next cycle. So an easy way to figure that out is whatever your remainder is, that's the derivative that you want. Now be careful, because when you divide, sometimes you get a remainder of 0, right? If you get a remainder of 0, that means that you want the original function before you ever took a derivative. So if you got a remainder of 0, that would just mean go back to the original function. All right, so here is our homework for tonight.